as soon as possible. I will be talking about monitoring principles.
Okay. This can be also for the other days?
No,
Okay, you see.
Some of you might know me. I'm Miloš Davidović. I'm in charge of
this process.
Yeah, just make a presentation on PowerPoint first. Okay.
I didn't.
This is a summary of the talk.
Maybe.
First, I'll talk about basic
Nice.
physics.
Okay.
Basic physics of aerosol particles.
Short presentation.
Then I will talk about various measuring systems that we can use to measure concentration with a particular method. That is, I will briefly talk about reference methods. Then I will focus on the systems that can provide more temporary resolution, these kinds of measurements, and that can give you actually the size distribution of the particular method, that is SNPS and OPS measuring systems. I will talk about various parts of that kind of system, inlet, charging chamber, DMA, CPC, and so on. And then I will briefly talk about low-cost measuring system and how they relate to these more complex systems and how they share some of their operating principles and also some of the drawbacks. And I will also highlight the advantages of the low-cost measuring system. So, when we say aerosol, we must keep in mind that it's a complex phenomenon. Aerosol particles range widely in size, 5 orders of magnitude, from about 1 nanometers to about 200 micrometers. The basic definition of aerosol is a solid or liquid particle suspended in air. These size ranges are determined by several factors. If you go for the larger particles, they can't actually be suspended in air for long, so they're not interested in as aerosol particles. And if you go to the smaller particles, after some range you run into more molecules. Solid particles and small and so on. Larger particles are typically created by mechanical processes. You can have like mining dust, asbestos fibers. You can also have larger biological spores. These go in size from 1 micrometer to a few hundred micrometers. Then you can have biological bioaerosols, for example, bacteria. They are roughly sized from 5 micrometers to 10 micrometers. Various urban aerosols. These are emissions from vehicles, from various industrial sources. All those particles create chemical reaction gases. These are roughly in size from several tens of nanometers to about 5 micrometers. You can have also viruses that go in size from 10 nanometers up to 100 nanometers. These are just a rough kind of categorization in order to keep in mind what kind of wide variety of aerosols. There is typically used categorization of particles that divides into the 2 different categories. You can have fine particles. These are particles that have diameter smaller than 2.5 micrometers. You have coarse particles. These are larger particles that have diameter smaller than 10 micrometers. And you also have ultra-fine particles. These are becoming more and more interesting because a large percentage of health effects is related to ultra-fine particles, and these are not necessarily covered by standard methods because ultra-fine particles, they have a small mass fraction, but they are actually enormous concentration that contributing a lot, and these other fine particles have diameter smaller than 1 millimeter. Interesting, you know, about
I will use the microphone.
okay, I will.
I love Earth and that will be
I will amplify myself.
I'm not sure it will help, but I think it's really the distance between your mouth and the microphone. You really need to, for most cases,
With this one, a little bit of bass. Yeah. Okay. For comparison, visible light has a wavelength of range depending on the color of the light from the range about 400 nanometers to 800 nanometers, and this is kind of number you want to keep in mind when you're thinking about optical particle sizes. That's kind of talking about because these are physical limitations of what you can detect with optical particle sizes. Of course, particles. When we talk about size of the particles, it's easy to define the size when you have spherical particles, but these particles are not spherical, they can come in various shapes and forms. And then we need to have precise definition of what we mean by diameter of particles. And just one additional complexity. Okay, particle formation. Now, basically, I mentioned before that the process in which particle, type of the process which creates the particle determines its size. So, on one side of the spectrum, well, for larger particles, we have mechanical processes. Energy is supplied to bulk material, for example, cutting, blasting, spraying, such things you have like in engineering and so on. And these are typically large particles. On the other hand, you have molecular processes such as nucleation, coagulation, and then condensation and evaporation. And here in this diagram, you can see how going from gas molecules, how you get growth of the particles, and how they in the processes of nucleation and coagulation, they can increase in size. The condensation is interesting, and some instruments actually use this principle of condensation to enlarge the particles, but I will talk about it more later. Now we continue to the physics of the particles. This will contain a lot of simplification, but I hope also to arrive at some insights and to better illustrate how some of the parts of the equipment work, why there are some losses in the sampling system, how you go about designing aerosol instrumentation. So, and this is clearly visible once you keep in mind the basic physics of particle dynamics. So we will discuss forces that can act on aerosol particles. We will start with gravity, then we will continue to Brownian motion, and then we will talk about how electrical fields can also influence particles. Some of these forces are important and dominant for smaller particles, some are important for larger particles, and once we understand this basic concept, we can have a better feel for what happens to our aerosol particle. So we start with gravity. What happens is particle has a mass, force of gravity acts on particle, but also on the other side it is suspended in air, so it has also drag force. The drag force depends on diameter of the particle, the velocity of the particle. So basically what we would expect, not knowing much about this, and that the particle will accelerate, reach some terminal velocity, and then continue to settle. And we may ask ourselves why don't aerosols particle just settle, and that way we can, if we wait long enough, we could actually solve air pollution phenomenon. And here I have a nice table illustrating what happens to the silica particle and what is if it has a standard density and so on. And depending on the size of this silica particle, if you have large silica particle, its terminal velocity is 0.7 meters per second, and during 1 minute it will settle along at 44 meters. That's good. Then if we decrease the diameter of the particle, for example, we go to 10 micron particle, then we can see that the terminal velocity is much smaller, and if we wait 1 minute, it will only settle about half a meter. And then if you go even smaller, you can see that the settling velocity is basically negligible, and that the particle stays suspended in air for very long. So that's why we can't just wait for the particles to settle. It has to do with gravity and or settling velocity and the back force of the air that is suspending the particle. Then we have inertia. So far, we will discuss airflow. But if we have airflow, then this drag force is a bit modified. You have the speed of the particle, but also the speed of airflow, and you arrive at the similar equations of motion here also. Important thing to keep in mind is characteristic time. That is time associated with the motion of the particle relaxation time, and stopping distance of the particle. That is the product of relaxation time and initial velocity. These kinds of things are important when you start, for example, designing impactors and various devices that need to like use this kind of properties of the particle to, for example, select for certain size of the particle. Now we're up to Brownian motion. This kind of motion is, as we will see, it is characteristic for the smaller particles, the dominant for the smaller particles. It's also discontinuous and random in nature. And here are the equations of motion, but don't go into details here. The important thing is to know that there is a diffusion coefficient that determines the amount of spread, so say spatial spread, that the ensemble of particles will experience if you wait a certain time. And we see that this spread is proportional to the inverse of the particle diameter. So the smaller the particle, the larger the spread over time, and that is basically the dominant form of motion for small particles, while the gravitational settling is dominant for large. And the last thing I will talk regarding this equation of motion for particles is particle in electric field. This is important because some of let me be precise, charged particles react to the electric field. And some of the instruments, for example, DMA classifiers, they use this property to actually, by applying certain strength of the field, to select for some of the particles. Also, we have here the velocity of the particle once it reaches steady state in some electric field is proportional to the size of the particle, and that way you can actually select for the size of the particle in these kinds of DMA classifiers. This is Frank talked about it a bit. Yeah, these are devices, inertial impactors and cycling. These are devices that you can use at the inlet of your sampling instrument to select for size of the particles or to collect particles of a certain size. And you can see how the physics that we described earlier works here in practice. For example, if you design this inlet with sharp edges, the air can follow, of course. The particles suspended in air, not so much. So the larger particles, due to inertia, will hit the impaction plate, while the smaller particles will continue to go with the air. Also, you can have like cyclones that are designed in a way that certain sizes of the particles use aerodynamic properties of the particle circle, while the size that you would want continues with the airflow to go further in the instrument. Another slide I like is regarding filters and much tubes. So how do we actually use filters to filter particles? These filters are typically made, for example, from like a mesh of fiber. And once you have a stream of air with a large particle content, a large particle in that stream air has high probability of hitting the fiber because the airflow will go around the fibers, but the large particles due to inertia can't follow. On the other hand, why small particles, they experience Brownian motion. So while they will go with the air, due to Brownian motion, they can have also high probability of attaching themselves to the fibers. But also there are medium particles around 200 nanometers which are minimally affected both by inertia and diffusion, and they actually can follow the flow. And these are kind of particles that are difficult to filter out. And basically, when you, for example, have HEPA filters, their burst performance is around that size range when you have particles which can follow the airflow maximally and not be affected by inertia. Similarly, in tubes, why do we have losses in tubing? That's important when you're doing some kind of measurements. You need to take care about the tubing that actually supplies the air sample to your instruments. Big particles will settle due to gravity. On the other hand, small particles will be due to Brownian motion, and medium-sized particles will just go with the path. We capture the tubing that's always something to aim for. Short recap of physics we mentioned. We had Newton's second law that was starting from the effects we have discussed. And we have discussed settling velocity. and that is connected to the issue that answers the question why don't aerosols just settle. Also, we discussed inertia of the particles and how is that important, for example, in designing impactors, in designing filters, and how particles can actually follow airflow and some can't because of light inertia. And we can also discuss force on particles, that is electrical field force, and that is important in some of the instruments that use DNA classifiers. And we have also discussed actual formation of the particles from both sides of the size spectrum, from smaller particles, how they're formed from gas, the processes of nucleation, coagulation, and from the larger size of the spectrum, how are they formed through mechanical processes. Now, I will just brief on almost 7 minutes. So, this is the schematics of an aerosol sampling system. We have aerosol, we have specially designed sampling inlet, and so on. Then you have some kind of sensing medium. And you have typically a pump that supplies that actually ensures stable flow. Frank was talking about the importance of having a stable flow because in the end we want to have precise information about concentration. Okay, so I will just briefly mention reference particle methods. Frank talked about this. This is a nice photo of a sphenolethyl pump. The kind we have in our lab, basically all over Serbia. The large thing there is the pump, and the smart thing is the head on the top, and it's the sampling head basically can select for size. It can either be designed for PM10 or PM2.5 particles. And then after you, for example, sample for 24 hours, and you collect particles on a filter, which have, of course, filters have suitable porosity and made up with different materials and so on. Basically, when you measure the difference in mass of filters and you have a total flow, you can determine the average concentration. Here is, despite this being the reference method, it has a bunch of drawbacks actually. First of all, it's you kind of have to do it. If you don't have the automatic system, you kind of have to do the manual thing of changing the filters. And in that process, you can actually damage the filters, and these scales that are used in lab are very sensitive. So you can basically, if you damage the filter, then you can't correctly measure the difference in mass. But that is on the handling side, and if you're a well-practiced technician, you can do this without that problem. But there are other problems like peculiar chemical composition of PM2.5, and it has like some volatile particular matter than the actual mass of the filter can change due to some other reasons. But the main drawback is that you get measurements that are average over 24 hours.
Miloš, sorry, I want to super important, but since you are speaking about that, the latest standard requires that you keep the exposed filters to a temperature under 23 degrees, just to avoid the losses of
The losses. Thank you for this. Yeah. Of course, the more careful the handling of the filter, the less problems you will have. But if you want to have like a larger temporal resolution, you need to use some kind of optical method. And here I have given the overview of the TSI instruments that we will be using in the exercises. It can detect particles from 300 nanometers up to 10 micrometers in 16 channel size bins. It has 1 liter per minute air sampling flow, and it uses scattering theory to calculate not only the number concentration, but also to determine the size of the particles. I need to mention here that this scattering theory is only for spherical particles, but as you have seen, not all particles are created equally spherical. So you basically get kind of equivalent optical diameter. That is the drawback of the optical method. And basically, since you're using additional assumptions, for example, if you have multimodal size distribution and not all modes have the same density, then you can kind of get into trouble when you start calculating mass concentration, because you don't know the precise density of the particles, you don't know precise size of the particles, but this is why these are all equivalent methods, and they are not measuring actual mass, they're like measuring equivalent mass using a number of starting assumptions. And this is the schematics of the optics chamber. You have air sample going in. It's designed in such a way that only one by one particle arrive in this optical chamber, and then they are illuminated with a laser, and then you collect this reflected light on spherical mirror, and based on that signal and a bunch of assumptions connected to mean theory, you determine the size of the particle. These are typically calibrated using polystyrene latex calibration curves, so you kind of get equivalent polystyrene latex diameter particles. But you can do a bunch of other calibration actions, so you're not necessarily needed this. This is the schematics of another instrument that we will use in the exercises. It covers the range of the smaller aerosol particles. This is nanoscan scanning really the particle sizes, and it can measure from 10 nanometers up to 400 nanometers. And at the end of this system, we again have optical components here, counting particles using optical method. But you need, because we are talking about very small particles, you need to do a bunch of preparation of this aerosol that's coming in order to be able to actually detect those kind of particles. So you start with the charger, why charger? Because and as I mentioned before, these kind of instruments, they use electric field to classify the particles. So you need to have charged particles, and you actually can only measure charged particles. So if the particles are neutral or they have the like positive charge, and the system is only measuring particles with negative charge, you need to prepare the air sample in some way, and so that's one issue to have in mind. So out of all aerosol that you have, you're only measuring a small fraction of like for example, negatively charged particles. And you need to prepare, because, for example, mu aerosol, uniform aerosol will not have a equilibrium state of charge, so you need to make that equilibrium somehow, and you do that with all charges. That's actually that first was a cyclone to eliminate very large particles. And then that continues to the DNA classifier, and that applies electric field and only selects for certain size of particles. And then you started from polydispersed aerosol and you arrived at monodispersed aerosol, but it's still very small particles, and if they go through the optical chamber, they will not get picked up by the detector. So you need to enlarge them, and we do that by actually enlarging them in a saturated alcohol vapor. And if the particles go through this saturated alcohol vapor, they act as centers of condensation, and alcohol condenses on them, and then spending some time in that saturated vapor, they are actually around enough so that it's integrated. That was basically that. This is how this instrument that we will use to measure sizes looks like. It's very compact and very complex on the inside. This is the larger version of the instruments that has basically all the same components as the small one, but it can measure, it has more capabilities. I have already talked about insulation particle counter. And we arrive at the called sensors. Just a few more slides. These are basically use the same principles that their larger cousins use, but they're much simpler. For example, this version, I think it doesn't even have a fan for air intake. It uses warm resistor to promote air intake. So it's very it has all the elements of the aerosol measuring system, but they're simplified to bare minimums. So you have some air intake, but it's not very nicely controlled as if you would have a lead brake pump. It has some kind of optical chamber, but it's not that nicely designed. Some of these instruments don't use, for example, even Mies scattering theory. So they kind of have just one signal from photometer, and that is calibrated in some way to measure urban aerosols. These low-cost instruments also have the slightly more advanced versions.
Sorry, Miloš, it looks like there's an alarm saying that you should turn on.
Yeah, that's you need to do something. Yeah, the TV is apparently. Yeah, it does.
Behind the laptop. Shut the TV. All right.
Never mind. Okay. There is a more advanced version of low-cost sensors, such as this alpha sensor we see. And these actually have a more sophisticated air intake. They use Mies scattering theory, so they can actually size the particles in large enough instances. So to arrive at the conclusions, we have seen the basic physics that illustrated some of the whys behind the design of the instruments and things. And then we have mentioned reference methods, which are very accurate, but needs to be supplemented with optical methods to give more temporal resolution. And low-cost sensors can give more spatial resolution. That is kind of a thing to keep in mind. So we have these reference methods which are expensive and give really nice results. Yeah, depending on the samples. Then you can have more temporal resolution using optical methods. And then with low-cost sensors, but these are still very expensive, and then with low-cost sensors that inherit some of the good sides of the optical methods, you can have more spatial resolution. But of course, always keep in mind that the accuracy is, as you progress to this low-cost sensor system, accuracy is increasing. So that's all. Thank you. So otherwise we can go direct to lunch.
Yeah. Can you give rough count, keep account of the different issues affecting low-cost sensors in comparison with those items with this equivalent methods? I think yesterday we were talking about Zoran. Zoran commented the hygroscopic effect affect the low-cost sensors, but does not affect gravimetric. Can you comment on this? Why? That will clarify.
So I'm not sure I understood the question, but the various shortcomings of various methods and how some things affect. Yeah.
For example, the hygroscopic effect.
Yeah. Or
Why does it affect the low-cost sensors? It does not affect the gravimetric.
Basically, it depends on the design of your experiment. And for example, you can also design an experiment where humidity will also affect your lab grid instruments. You don't attach the for example, in the recent campaign that we are still conducting, we are using napkin dryer. So that is a large tube filled with napkin, and it has its own vacuum pump, and it's quite costly. Around 5,000 euros, and it basically prepares the air sample to be specific with the specified temperature and specified humidity. So if you have very humid air, once it goes to this napkin dryer, it will in the end have desirable humidity and so on, and then you continue to your actual lab grade optical system. But if you have a low-cost sensor, it just immersed in the outside air, and it's at the mercy of the elements and so on. So it basically, but you could also attach napkin dryer to the low-cost, but it doesn't make much sense because, for example, this kind of dryer is 5,000 euros and low-cost system is hundreds of euros. So it doesn't kind of make sense to prepare air sample in such a fine manner and then attach it to the lower grade instruments. But so basically, low-cost systems, they have the elements of their more advanced cousins, so to say, but they're stripped to bare minimum, and that's why they have low cost. But you can improve on every aspect of that. For example, if you attach, for example, pump to the low-cost sensor, then you have a slightly more expensive low-cost sensor, but it also has a more controlled air intake, so you will get better measurements. So you can go and add up to
Because of the you can choose the
you can choose them.
If you have a gravimetric method, you are directly weighting in of the mass. When you go to mesometers, for example, the hygroscopic effect will disrupt the hypothesis on the density of the part. So there are these effects that should be taken into account when you look at the data
Yes. Okay. Okay, that will go to lunch. Thank you, guys.
It's